The next section continues with some basic circuits again, and these are latches, flip-flops, and registers, and we're going to look at a little bit of I/O as well. Anyway, for sequential logic, memory elements are needed to store the results. Typically a memory element would hold one bit, but could be arranged to form larger structures. The simplest memory element is that of a cross-couple latch, so basically it's a pair of inverters which are connected end to end. And the following is a little schematic representation of that. You can see why it latches that value. So if there's a 0 here, there's a 1 here, and it's reinforced by that cross couple of the latching. My question you might ask is, what if there are 3 inverters in a circle arrangement? Well, you should be able to sort of rationalize that perhaps what you formed then is a ring oscillator. If you cascade some latches together, you're going to basically end up with something that resembles a flip-flop. And in this particular case, they're shown with the inverters, which are a cross-couple latch, as well as some transmission gates out here. So the transmission gates, as you recall, had both the N and the P-type transistor, and these are active on different phases of phi. This previous figure still required overpowering the feedback loop, but you could also introduce a switch in here and a switch in here, which is complementary to this switch here. This would be complementary to this switch here, in which case this basically becomes a schematic of a positive edge triggered D-type flip-flop. And one thing to point out is that D flip-flops are pervasive in all modern circuits, and there's always trade-offs. For example, there may or may not be a transmission gate. You might just use an N-type transistor effectively functioning as a switch. And over here is a little schematic representation for our edge-triggered D-type flip-flop. So just continuing on a little bit, this is one particular style. There's 2 transmission gates that are used for each latch, and basically denote at phi and phi bar. So when the clock is high, phi is equal to 1, and this sort of illustrates the feedback paths which are in operation, or the feedback path which is broken, and you get basically whatever value is held here, the complement on the output. Similarly, if phi goes low, then what we're going to do is we're basically turning on this transmission gate. This guy is disconnected, so you don't have to overpower it to change its state, and the output is totally separated from the input, or isolated from the input. Here's an example of what a layout might look like for that. Somebody went to the trouble of laying that out with showing some of the fundamental transistors and some of the lower levels of detail. Again, this would be done with CAD tools, and someone would be trying to squeeze out the minimum area to make a small device as possible. This supposedly was a transistor level schematic of the following figure, or the previous layout rather, of our D-type flip-flop. Anyway, it gives a nice opportunity to give an in-class assignment and basically see if you can correct this figure, because there's clearly some things that are wrong with it. Once you have D-type flip-flops, you can easily build shift registers, linear feedback shift registers, counters, etc. And here's an example of a shift register, and here's an example of a linear feedback shift register. And this basically are just taps being brought back from different values of the outputs, and it'll form a linear feedback shift register that, depending on how it's configured, may provide a maximal length sequence or something of that nature that you'd find in many types of circuits. Certainly once you have the memory element, you can certainly build any finite state machine you like. And here's this schematic representation of it, where you'd have let's say some inputs, a clock and a memory element which is holding the next state, which can be S bits wide, and input maybe N bits wide, output maybe M bits wide, and basically the combination of the memory element and the combinational logic will provide the next state, as well as whatever the input happens to be. Popular encodings might be minimally or maximally encoded, and the maximally encoded is typically called 1 hot. Finite state machines are certainly well suited for Verilog, and very complicated finite state machines can be designed, simulated, and synthesized using Verilog. Here's a really nice example of a lab that was written, I guess, by, I think, William Daly. Provides an excellent example of the infamous traffic light controller, written in both structural and behavioral Verilog. And you might want to go through that, because he also points out a number of useful things to do when you're writing Verilog code for a finite state machine, sort of code rules or code design rules. Moving along a little bit to some input-output pads. Basically, what we might recall is that we internally on the chip we have some fairly small devices, and this outside world is a harsh place, and you can get basically over and under voltages on the pad, and these would typically, probably without much difficulty, kind of blow up these devices internal here if you didn't provide for some type of protection. So in this particular case, there's a current limiting resistor, and there's a couple of protection diodes. So in the event of an overshoot, let's say you had a transmission kind of like ringing on this pad, the voltage on the input would go above VDD. Basically, you'd turn on this diode, and you'd basically sink all that current, that excess current, to VDD. Similarly, this is the layout of it with shown in a little bit more detail. Similarly, if the voltage on the input went below VSS or well below ground, what happens here is then that current then basically ends up going to ground, or if you want to think of it as positive current, it'll flow from the ground to the pad. But in any event, it protects this part of the circuit from severe undervoltage, in which case it would also be detrimental to this internal circuit, which are minimum size dimension devices. This is what some of the I/O pad structure might look like if you cut through it, showing the wells that are the P-type guard rings and the N-type guard rings, and what they're, the voltages they're tied to, and the idea being that any of these excess currents and over voltage on the pad, for example, would turn on this device in N well, which is a PN junction, and then the current would be going to VDD and protect it from the internal circuitry. So certainly they're very complicated structures, no doubt about it. Here's an example of a couple of input-output layouts. Some things are recognizable on it, some perhaps a little less so. But this kind of structure here kind of shows how you have, on an input pad, you have a bunch of protection circuitry so that whatever's sitting down here is not going to see any over voltage or under voltage on that pad. And this would be the pad that the wire is bonded to, off to the basically a pin on the chip, or a lead on the chip. Here's an output pad, and it's not particularly recognizable here, but basically it's a series of increasingly larger inverters, and these inverters typically scale by some ratio close to E. You can sort of do some simple calculations, and we may later, and you'll see that it works out to E, but it's kind of flat, so it might be 2, 3, or 4. But in any event, you cascade some inverters so that you have sufficient drive to go to the outside world. If you're driving for a minimum size device, it would sort of take you forever for a rise and fall time, because as you can imagine, the capacitance of this and whatever it's connected to is going to be relatively significant. So that was sort of things I just mentioned. You have to have sufficient drive strength on the output pad, so typically you have a number of inverters and they're cascaded together, with the next being some scaled up version of the one before it. You could also have bidirectional I/O pads, so in this particular case you have the opportunity to tri-state this, make this look like high impedance. This is one example of how you might do it. I'm sure if you look on the web you'll find a number of other means of doing this. There is an error down here which I'll point out, and the question then becomes, what's wrong with this circuit? As I said, this is sort of one means of implementing these types of protection devices, and it should be relatively apparent how this would work if it were connected up properly. So basically on the output we have tri-state control. The enabled output, enabled 0 we get high impedance and can use the input. Enabled equal 1 we get a non-inverting buffer for the data output. The input, we had a FET there which was supposed to be a follower to limit the current, although it's not connected up properly. A resistor which limits the current, and a diode which limits the voltage again. This is an example of an I/O pad from a university type service which is known as MOSIS. It probably still exists, I don't know for sure, but this technology is certainly very, very old, 1.6 microns, and it just illustrates sort of how complicated these things tend to be, and a fair bit of skill probably in designing these devices. But this is an example from a textbook which is probably very old, but illustrates sort of the complexity on building guard rings. Newer devices might even have a little bit more programmability, so that you'd be able to control things such as the slew rate, for example. And at this point in time, I'll take another small break.